This is same tree, LeetCode 100. We have two different binary trees, and we have to determine if they are identical in terms of structure and in terms of values for their nodes. So this here is a tree 1, 2, 3, and this is another one 1, 2, 3. They have the same structure and they also have the same values. So where we have 1 in the first tree, we also have 1 in the second tree. Where we have 2 as the left child in the first tree, we have the same thing in the second tree. And where we have the number 3 is the same thing in the second tree. Here we have equal values, the same ones, 1 and 2 in the first tree and 1 and 2 in the second tree, but the structure is different. In the first tree, 2 is the left child of the root nodes with the value number 1. In the second tree, 2 is the right child of the root nodes with a value of 1. So this here would be false because we have to return a Boolean value. In this third example, we have 1, 2, and 1, 1, 1, and 2. The values are the same, but not in the exact same positions because the structure is identical. We have a root node with two child nodes, left child and right child, but where the 2 and the 1s are as values are different among the trees. We need to consider something. Whenever there are no child nodes, left child nodes especially, you're going to have the value null inside of the input array. So here in this example, we have the root nodes number 1 for the second tree, and the left child is null because there's nothing there. So where we have 2 in the array means that this is the right child of the root nodes. Now, we're not actually getting arrays as inputs in this challenge. Instead, we're getting the tree nodes pointers for our different trees. Here we have a function, a Boolean one called isSameTree. We need to return true or false. The first pointer is the root nodes of the first tree, and the second pointer is the root nodes of the second tree. So if you look at the structure of a tree node, it's like this, very basic. Every node has a value. It can have a left or right child as a node pointer. And every node can be initialized with a value of 0, and the left and right child nodes are null pointers. We can also assign a value to a node when we're creating one, and we can also determine how that node is connected. So we can pass a value to that node and also associate different nodes as the left and right child nodes. For this solution, I am using level order traversal. It's an algorithm based on that. So before I proceed, I want to refresh your memory very quickly on level order traversal. We can also call it breadth first search or BFS. So if you look at level order traversal, this is a website called enjoyalgorithms.com. You can see the logo here on my screen. So they have a very simple structure for how that algorithm works. First, you pass in a node as a parameter. It's a root node. You check if that node is null, then you return. Otherwise, you create a queue that can store nodes, and then you enqueue the first node in your tree, which is the root node. After that, you're going to check, so long as your queue is not empty, you need to remove the first node and then add to the queue the left and right child nodes of the root nodes that you just removed. So at the next iteration, the queue is going to be filled with the left and child nodes of what was previously the root nodes. And you're going to keep doing that. Anytime you visit a node, you add to the queue that node's right and left child nodes. This is going to let you traverse the tree by levels, from the root nodes to the direct child nodes to the child nodes of these child nodes, and so on. So you can pause the video and have a look at this here on my screen. Otherwise, I'll just proceed. In my case, I'm using a stack in C++, and that stack can store node pointers. That's why I have 3 nodes and then a pointer. It's the same type as the parameters here. The first stack is for the first tree, and I'm calling it P stack. And the second stack is for the second tree. I'm calling it Q stack because the nodes here have the name P and Q. So at first, I add to my stack both root nodes for the respective trees. And then I create a while loop here and I check, so long as both stacks are not empty, I can proceed with my conditions and my traversal. So I need to grab the root nodes or the nodes that I just added, those that are at the top of my stack. For my first tree, I'm calling that extracted nodes temp P. And for the second tree, I'm calling the extracted nodes temp Q. Because we are checking for the structure, if it's identical between the two trees, they always need to be valid or invalid at the same time. So here, if temp P is a valid node, but temp Q is a null pointer, meaning that there is no node there, it could be null, then we have to return false. Meaning that at this point, we don't need to process anything anymore. We know that the structure is different. The same thing applies if temp P is null, but temp Q is a valid node. We also return false. So this return statement addresses both conditions here. We also need to verify that if both nodes are null, like I explained here, we have null here in the inputs. So if both nodes are null, we just remove them from the stack. And we continue with the algorithm by processing the other nodes on both stacks. So that is what we are handling right here. And we also need to check if the values are the same, because we're not just checking for the structure, but also for the values. So if in the stacks, as we are processing them, we encounter different values for temp P and temp Q, then we can also stop everything and return false. Otherwise, if both nodes are valid at the same time and their values are the same, we can continue to traverse our binary trees by level, which is the BFS algorithm. And we do that by removing the front nodes in both stacks. So in here, in the examples, they use DQ and then they get the extracted node directly. In our case here, we first get the top nodes in the two stacks and then we pop them off right here. So now that we've popped up those nodes, we now have their child nodes left in the stacks. So to do that, we push the left node and the right node. These are the child nodes of whatever node we just removed. So we do this for the first binary tree using P stack, and we do this for the second tree using Q stack. We're going to process both binary trees, and they should work fine until the stacks are empty. And if we were able to process everything, then we can return true because we never return false during this logic here. So it means that the structure and the values were the same. Note that in my case, unlike the typical level order traversal algorithm, I am pushing every node on the stack regardless whether they are null or not. In this case here, you see that they always check if the left child is null, don't do anything, but if it's not null, then you can add it to the queue. Same thing for the right child. They check first. If it's not null, add it to the queue. In my case, I'm adding everything, including null nodes, because of this condition that I have here at the top. We need to make sure that both trees are structurally identical. So this means that if a node is null in one, but not in the other, then we need to return false. So we need to know where the nodes are not valid. That's why I'm adding everything in here like this, without having if statements to restrict the addition on the stack to valid nodes. I'm adding everything, including the null nodes. So I hope that this logic is clear to you guys. Let's run the first test case. Now let's use all the example test cases before we submit it. So we've passed everything. Now we can just submit. Sometimes the code is very fast. So 9 milliseconds in this case. Previously we had 0 milliseconds and so on. But I'm going to accept this. You guys can optimize my code here to make it even faster if you want. But so far, that is it for my LeetCode solution to the challenge called Same Tree. That was LeetCode 100. If you like my solution in C++ and you want more coding interview questions to practice, please subscribe to my channel and I'll catch you next time.